So welcome, thank you for attending. My name is Scott Gordon. I'm a tech lead, a data engineer at 8451 on our clickstream data product team.
And my name is Allie Hanlon, and I'm a data engineer at 8451 as well on Scott's team working on clickstream data.
So what we're going to show you this afternoon is actually two different solutions. Both of them were built using Delta Live tables, or DLT, and each of these solutions is going to showcase a different feature, different piece of functionality in the tool. First of all, a little bit about 8451. So we are the market research, data analytics, and data science branch of the nationwide grocery retailer Kroger. Allie and I are data engineers on an enterprise data product team that deals mostly with digital shopping behavior.
Okay.
So Allie's going to talk about the first feature.
Awesome. So I'll be walking us through the first feature that we'll be talking about today, specifically how we use change data capture and apply changes, and within that, the once flow feature to run apply changes one time on a static source. For those of you who may be unfamiliar with apply changes, you can think of it as the DLT version of a SQL merge into statement. So not only is it able to handle appends or inserts, but it can also handle updates or deletions based on the conditions that you set. So the use case in which we use this was the migration from an on-prem legacy data flow in Hadoop to Azure Databricks. We were creating an entirely new DLT pipeline that needed to replicate the logic of the on-prem solution. So not only did our data flow or our pipeline have to read from an ongoing stream going forward, but we also needed to take all of that history data that our on-prem solution had processed in the past and bring that into our DLT solution as well. And we were able to do so using apply changes and the once flow functionality. So to provide just a little bit of background before we dive into the pipeline and the code, this solution specifically handles online order data. So as Scott mentioned, our team works a lot with digital shopper behavior. And so when you go to a Kroger website or a Kroger app, you have the option to order groceries for in-store pickup or delivery to your home. And so this solution was processing data associated with those orders. And to show a quick example or kind of a simplified schema of what you might see with that type of data, you'll see we have an order ID as well as an order status, maybe when the order was created, updated, who submitted the order, if it was a pickup, delivery, and then the items that were included in it. One column that I'll call out here is that status column. So both of these example records show complete, but in our kind of raw data feed, we're getting all of the creations, updates, cancellations, completions that happen. So we're receiving multiple records with the same order ID, but our end users that use this data in our data product really only care about the final state of the order. They don't care if someone had 8 ounces of strawberries and then switched it out for 16. They just care what the final state was. So keep that in mind. It was one of the main reasons that we looked at and decided to use apply changes. So starting out just with an overview of our legacy Hadoop solution, you'll notice that there's 2 distinct parts of this solution. So there is a flow or a section that is managed by our in-house data ingestion team, and then there is a section that is managed by us, the data mart team. Essentially, the in-house data ingestion team would read the Kafka order activity stream. They would then use NiFi to ingest and create files that were then processed in a daily batch job in Apache Airflow, and then ultimately output into our final data mart tables by our team. So not necessarily ideal to have this split up between 2 teams as well as in a batch process. And when we made that switch to DLT in Databricks, it significantly simplified this solution. So right off the bat in our DLT architecture, you'll notice that there is only one process, so we were able to condense this down to be managed fully by our team. In DLT, we're able to read directly from Kafka and Event Hubs to get that order activity stream directly through DLT, processed, and then output into our final Delta Lake tables. You'll also notice that second data source or second flow, the history data, So as I mentioned, we needed a way to get all of our on-prem data that had been previously processed through this solution as well. Kafka only has the most recent or kind of a limited new amount of data, and we needed all of the previous months and years that our on-prem solution had already processed. And so this is a static source that we added to this flow to be able to get all of that into our final solution. So taking a look now at the pipeline overview. So once we built the pipeline in DLT, you'll see that we have two views that feed into a final streaming table. So the first view is what I would consider the online order view. So this is attached to Kafka. This is kind of that ongoing flow of data that we'll be reading from here on out. The legacy view is that history data, so that static history source of all of our data from on-prem that we are reading. Both of these views feed into our final online order streaming table, and both of them are brought into this table using apply changes. So as I mentioned, apply changes is kind of like a SQL merge, and so we're essentially merging this data from the Kafka source and from our history source into a final table. You may ask, why didn't we just append our legacy source? You know, it's already been processed, there shouldn't be any duplicates. But we wanted to make sure that the legacy data and the Kafka flow had all of the data, but also did not have any overlap. So we don't want records showing up in our final table that maybe were included in both, because we wanted to make sure we were fully encompassing all dates. So I will skip ahead and we'll actually look at an example code snippet of how we used apply changes for both of these views. So we had two distinct apply changes blocks, one for our Kafka kind of ongoing flow, and then one for our history data. So this is the one that would be associated with the kind of ongoing Kafka flow. So you can think about kind of this format as we are taking a source table, so the online order view, and we are merging it into a target table, which is that online order completed kind of final streaming table. And in our case, we set the key to be the order ID because we wanted the unique identifier in our final table to be the order ID. We only wanted one instance of each order ID to appear in the end. And in order to tell DLT which record or which order ID record to pick to put in the final table, we specified a sequence by. So we have it sequencing by the last updated timestamp, meaning that if a new record were to come in with a more recent update or a more recent timestamp, that would then be updated in our final table. And then finally, in apply changes, you're able to specify a change data capture type. So we had specified that this data will be stored as SCD, or slowly changing dimension type 1, meaning that any records that are updated would simply be overwritten in our final table. If we had specified SCD type 2, it would retain the history of the table as well. So when an update would occur, it would maintain the original record as well as a new record with the updated value for historical or reporting purposes. In our case, we didn't need that, and so we just opted to go with SCD type 1. So to show an example on that previous sample data of how this apply changes block might behave, if we got these two records, they have the same order ID, essentially all of the same information in this case. Perhaps, maybe there was an item swap and the user decided to, use a different item in their final order. We would have apply changes pick the first record to persist. So if the second record already existed, it would be updated with the first, because the last updated time is more recent. So the first record came in on May 17th, whereas the other came in on May 15th. And because we sequenced by the last updated timestamp, apply changes will pick this first record to persist or to update. Similarly, if we receive two records of the exact same values, so for some reason, maybe there was something that happened, we got two records that exactly matched, apply changes would also take care of this and only persist one of these records in our final table. So looking now at our second apply changes block, this is what we used when we merged the legacy view or the legacy flow into our final table. It is essentially the same as the previous one, but there is one difference highlighted there in yellow, which is that we have set the once option equal to true. Because this is a static source, it's really not something that we need DLT to continually scan or continually merge into our final table. We just need it to run once, take that history data, bring it into that final table, and then once it's done, it is done. This was helpful for our team specifically because we didn't have to go back and do some kind of code change to remove this flow once it completed. We knew that by specifying the once option to be true, this flow would run one time and we wouldn't have to go back and comment it out or kind of try to make it seem as though it was there and we knew what happened, but it didn't need to be running continuously going forward. So we found this feature to be very helpful in this specific case because we're both trying to read from a stream as well as read from a static source in the same data flow. So just in summary, looking at this migration as a whole, migrating to Databricks and to DLT significantly simplified our data flow. It allowed us to manage this process by one team. And on top of that, we learned that DLT code is declarative, and so it's relatively easy to read, to maintain, even for a more complex use case. And then on the side of apply changes and using the once flow, apply changes gave us the ability to read from both an ongoing flow and a static source with no overlap between the two in the final table, as well as, of course, remove any duplicates or any other updates that needed to occur. And then it also allowed us to set that static source to run only one time, which was useful for us to prevent an additional code change later on in production. So with that, I will pass it over to Scott to talk about our second solution and our second feature.
Okay, thank you, Allie. Nice job. And we will have time at the end for questions. So if you've got questions about Allie's content, I believe we'll have plenty of time at the end to go through both of these if you like. So in this next solution we built, we took advantage of the append flow functionality. So append flow is a component you add into your data flow that allows you to have multiple source data sets flowing into the same target table. In our example, our use case, we used it a little differently in that we used it to change our pipeline over from one data source to another data source. We had batch files, JSON files that were loading into this solution, and we wanted to switch to a true streaming source. So this append flow functionality allowed us to do that. The data, again, is similar to what Allie had mentioned. This clickstream data that flows through this pipeline all comes from Kroger's online shopping apps, be it their Kroger.com site or any of their banner sites, Fry's, Dillon's, all those, as well as the mobile app. So this is all shopping behavior. So the normal searching for a product, adding an item to your cart, maybe searching coupons and clipping coupons, and finally submitting an order for either store pickup or delivery to your home. So our setup in this data solution was pretty similar, again, to what Allie had described for the order flow, but this was all clickstream flow. But again, we had this centralized data ingestion team who was responsible for bringing data into our company. So they used Apache NiFi, read from Kafka, read all those events, and put them into files. So they were separating them out into JSON files and then storing those files. This process actually ran in an on-prem Hadoop cluster. So they would then take those files and copy them up to Azure Blob Storage, where they became available for us. So our first version of this DLT pipeline we built was using the autoloader functionality built into DLT to read those JSON files, run it through all of our transformations, and produce, our MART tables. This is what the pipeline looked like in DLT. The only really significant thing we're going to talk about is this first table over here to the left in the medallion architecture. That's the bronze table. That's where all this data is flowing into, and the name of that table is actions. So all the flows I'm going to talk about from here on out are this actions flow. Here's what the code looked like, pretty straightforward. As Allie mentioned, the code is highly declarative in the DLT environment. So with a few simple statements, you can invoke an awful lot of functionality. So we're doing a Spark read stream here, format cloud files. So all you got to do to invoke autoloader is specify format cloud files. That activates this autoloader engine kind of behind the scenes, and all autoloader is doing is watching the directory that we pointed it to here. So it's watching this path and waiting for files to arrive. It's taking care of all the checkpointing. It knows which files are new, which ones are old, which ones have been loaded, which ones have not. So all of that checkpointing and exactly once delivery kind of stuff all happens behind the scenes, and it's handled for you. That, if I can successfully get back to that slide, so that load path was specifically this blob storage path right here, just pointing out to a container in a storage account in Azure storage. So that was version 1. What we wanted to improve upon there, though, was, again, we had this reliance on an external data team to handle the data. We really wanted to own the flow end to end. And we mainly wanted that because we wanted to reduce the latency. So this on-prem ingestion process and then collecting the files and copying up to Azure, that actually introduced a few hours of latency into the data. And we knew that if we could tap directly into Kafka, we could greatly reduce that latency. However, we couldn't simply take our pipeline, stop reading the files, point it to Kafka, and start it up at Kafka, because at that point we don't know what record did we leave off on, right? The checkpoints would be mismatched at that point. We may have missed some data. We may have loaded the same event from both feeds. We'd have no way of knowing. So that's where this append flow came into play. So we were kind of sitting with this dilemma on, how do we add this in? And we'd been working with one of the Databricks engineers, a solution architect. I'll call her out. Kudos. Shu Lee was her name. She'd been working with us to kind of help us with our DLT development. And once we described this problem, she said, lo and behold, we have this feature in preview that I think may solve your problem here. And that feature was the append flow. It is now generally available, but back when we built this, it was still in preview. So what we added in was the append flow. So we attached the append flow to event hubs or Kafka in Azure and started bringing these same events in through that second flow. While we were still running the autoloader process to load these files, to keep from duplicating data, all we had to do was put in a filter on each of these. So we put in a filter of, in this case, for example, April 1st. Say we only want events through this flow that are older than April 1st, and on this flow, filter out or keep only events that are on or after April 1st. I'll show you more about how we actually implemented that in the code. So we have our original flow up here. So again, this was the actions flow that existed, cloud files using autoloader. All we did was add in this where clause to say, only keep events earlier than April 1st. We added in append flow, the key word append here. Append has to append to something. So you tell it what flow is it appending to. It's appending to the actions flow. So it knows it's appending to this same data flow defined above, doing a read stream format Kafka. And here's our filter down here to only take events greater than or equal to April 1st. So what that looked like, the key thing I really want to point out here in this the explanation of this solution was that this pipeline ran in continuous mode, which means it ran 24/7. It was not a scheduled thing, right? Once we started this pipeline, it ran for months. And that was the real challenge of how do we switch it from one data source to another without interrupting that data flow, right? We didn't want downtime in the solution. So let me walk through how we actually deployed all these changes. So the solution was in production in its V1 version for actually a number of months, but for this example, let's just say 10 weeks, it ran that way. Then we add in version 2 of the code is where we add in the append flow, the second flow now reading from Kafka. We roll that out to production. It starts running immediately. However, we haven't reached the April 1st date yet. So at this point, all of the records coming through autoloader are still getting into the target table, and all the records coming in the new Kafka feed are just getting dropped, getting filtered out. So that continues to run. Finally, we get to the next week where we actually hit that cutover date. And again, here, think of this cutover date not as a calendar date, like the flow switches from A to B at that point. It's based on a date in the data. So you still have data flowing through both flows. And in this example, we can have late arriving events, right? Someone could be on their phone, loading coupons, doing whatever, all of a sudden battery dies, right? They're on vacation, whatever, they don't get their phone charged up and started to the next day. We're not going to get that activity off their phone until, the next day. So we can have, some amount of delay. So again, that was the key point of having both of these flows running at the same time and simply filtering on a date to make sure any single event only made it to our target table from one flow or the other and not both. So we left that running, V2 running in production for some amount of time, about another week, until we got to the point where we just knew, okay, there's not going to be any more late arriving data more than a week old. That's just not going to happen. So then we deployed version 3. Again, each of these deployments was a deployment. We used GitHub Actions workflows to deploy these. So when it would deploy the code, it would immediately stop the pipeline, apply the new version of the code, and restart the pipeline. So any deployment from V1 to V2 only incurred about maybe 4 or 5 minutes of downtime while the new compute is starting for the updated cluster. So let's take a look at version 3 then. So we don't want to leave autoloader running forever, right? Obviously, you're incurring some compute costs there. It's looking at that directory, waiting for files. We knew we didn't need to do that anymore. So now we want to take that original flow out and just leave only the event hubs flow running. So I'll show you what that code looked like. Again, key word of an append flow is it has to append to something. So we couldn't simply rip out the actions flow or we'd have nothing to append to. But this little statement right here helped us do that. So create streaming table, actions, that defines a flow named actions, but there's no activity behind it. It's just a name to hang on to. So the append flow is still appending to actions, still reading from Kafka. At this point, we no longer need the filter. We want 100% of the data flowing through this flow. So rolled that version out, and that took effect. All right, so the benefits of this was, again, end-to-end ownership of our data. We could read right from the stream all the way through our MART. The key benefit was reducing the latency of this data flow. Again, we used to see around 2 hours of latency when we had all the on-prem ingestion happening and copying, uploading of files to the cloud and all that. So by removing all that, we actually took the latency of this data down to, it averages actually about 60 seconds, we've noticed, from the time the click is captured to the time it's published in our bronze table. Migrated from the batch JSON files to a true streaming solution. Again, just the really key thing I want to point out about why we went about it with an append flow was to do this with no downtime to our end users. They didn't experience any SLA changes or anything noticeable stop of flow of data to our end users. And again, the nice declarative code was, it was actually fairly simple to add in a second flow and remove the first one coding-wise. Okay, so we're going to recap and compare and contrast these two changes.
Yeah.
You want that, or you're good?
You can
all right.
Yeah. So yeah, you might look at both of these examples and you see two data flows flowing into one final table. And you might ask, in what case would I need to use apply changes, and in what case would I want to use an append flow? So I'll recap apply changes and Scott will recap the append flow. But essentially, apply changes is very similar to a merge into, and so it is best for use cases where you have to handle inserts, updates, and or deletes. It has change data capture, so you can use change data capture type 1 or type 2. One caveat, because it is a merge, is that the schemas must match. And so if you have mismatched schemas or you have tables that are coming from different sources and the schemas aren't going to match, you won't be able to do a merge into that final table unless the schemas are the same. And then, of course, it has that once flow option built in, so you're able to run it one time on a static source if you so choose.
To add on to that, so in that scenario, the history data, actually schema didn't exactly match the new streaming data coming in, but obviously with some coding, some views beforehand, you can obviously merge the data to make it match. But the key point is by the time those two come together in the append or the apply changes, at that point the schemas must match. So contrast that to an append flow. An append flow is similar to, in the SQL language, a union all. So you're simply unioning two data sets with no sorting, distinctness. It's a full union all of the two flows. It does not support change data capture as applied changes does. However, in this case, the schemas don't have to be identical. So it will handle if one of the flows has an additional column that's not in the other flow, that's okay. Those can still be appended or unioned together. It'll union them by name, so it'll match the column names where they match. Now, of course, the schemas must at least be compatible. You can't have conflicting data types or something like that that would make the whole data set invalid. But as long as they don't conflict, it will handle differences in the schema. And also, there's no once option on the append flow. It's always there. Thank you, everyone. Appreciate it.